that I was trying to get across didn't quite come across in the formulas. I'm not sure, but in any case, let me just state it in words. So it's, if you like, a form of the equivalence principle, and it says the idea is that an infinitesimal neighborhood of a point in space-time is indistinguishable from an infinitesimal neighborhood of a point in Minkowski space. So this is a shorthand for neighborhood of a point in space-time, so which we've been calling M, is indistinguishable from an infinitesimal neighborhood of a point in Minkowski space. So this is the curved space, the general curved space-time of general relativity. And this, of course, is the space-time of special relativity. So let me just put that there. That's what's behind all the calculations. And you can think of it as a kind of form of the equivalence principle. And it's also obviously connected strongly to the idea of locality, which, if you remember, sort of in the first or second lecture, we were talking about how one of the ideas behind special relativity, behind general relativity, is locality. So this is an extreme form of locality, where you have infinitesimal neighborhoods. Okay, so now that we've set up a lot of the, not unfortunately all the formalism that we need, but a lot of what we need. In particular, we have the line element, we have the notion of vectors, we have the notion of inner product between two vectors, tangent vectors. So we can talk about angles, we can talk about orthogonality. So we have enough now that we can talk about what you might call reference frames, which, so that's what I want to do for the next lecture or so. So we might call it exploring the metric with the aid of matter. You could give other names. You could say we're talking about reference frames, or you could say we're talking about the coupling of the metric to matter. Remember, always in this special terminology where matter means everything but the metric. And you could also say that you're talking about the effect that the metric has on the behavior of matter. So you could say all those different things. And the form of matter that we'll be talking about is some idealized one, which are clocks, point particles, and along with clocks you might put rulers or measuring rods, often called rods, meaning things are measuring spatial distance, but not, at this stage, not yet talking about extended objects or fluids, or such as fluids or fields, matter fields. Okay. So in particular, we'll do an initial treatment of understanding the geodesic motion of particles. So I already gave you, I think last time, some things to read. I won't repeat them. So in doing this, we'll use, in effect, a couple of assumptions, or what you might call postulates, which, in a sense, also are disguised definitions. So when we talk about clocks, we'll assume, by definition, that they read proper time, right? So this d tau that we've been talking about represents the elapsed time along a world line of a clock. Of course, we'll idealize the clock as a point object, even though in the end that's really not consistent. And we'll assume that rulers, or what I called before rods, measuring rods, rulers measure orthogonal distance between what you might call adjacent world lines, infinitely nearby world lines. So for now, we'll just make this as an assumption. Of course, when you have a more complete theory, you'll turn this around and say that this is essentially a definition of a good clock and a good ruler. And then the point will be to prove that there actually are good clocks and good rulers. And hopefully that can be done, although when you come to quantum gravity, it's very doubtful whether it actually can be done. And that's one of there are arguments that it cannot actually be done, that there are fundamental limits to how accurate you can make clocks, and how accurately you can make localized clocks run. And that's one of the arguments people give for believing that probably space-time as we know it from the classical theory gives way to something else when you get near the Planck scale. Also, one comment here is that our postulates, these two postulates that I made here, are related, right? They're really things that have to do with special relativity, because it's in an infinite, it's in a neighborhood. The clocks the clocks we're talking about are ticking off local time, and the measuring rods we're talking about are measuring only well-defined for infinitesimal distances. So it's basically the same basic fact. It's the equivalence principle, if you like. And I just want to point out that these two assumptions are actually closely related to each other, as you can see in flat space. So let's make a little diagram in flat space. Suppose you have 2 point events, P and Q, along the world, some sort of inertial world line, some straight line, time-like world line, and you have access to a clock, and you want to know the distance to some other event, the spatial distance in your reference frame to some other event, which I'll call R. So how do you do it? Well, one way, of course, you can try and build ruler and so on, but a simple way using light and a clock only, of course, is to use the way we measure the distance to the planets and so on, the distance to the moon, and I guess the way the GPS essentially measures distance also, is just to time signal. So you send out a light signal. It just arrives exactly at this event R, and then it returns a light signal. And then you look at the elapsed time, and you say that in your frame, this event R is simultaneous, since the travel time out and back should be equal. In your frame, you say that this event R is simultaneous to the event that was halfway between the emission and the return, the reception of the return light or photon. And then the geometry of Minkowski space tells you, so this means that S is P plus Q over 2 using vector notation. And the geometry of Minkowski space tells you that that's so if and only if this line and this line are orthogonal, right? I mean, you can just see it in the picture, but you could do a calculation if you like. That's if and only if Q minus P, which is your phore velocity, the direction of your phore velocity, is orthogonal to R minus S, which is this which is this line, this space-like geodesic joining the two simultaneous points with respect to your reference frame, R, the event you're interested in, and the midway event on your world line. And then when that's true, again, this is the same simple geometry, you can check that it means that the norm of all these, these are right triangles, and the length of this, the length of this, and the length of this are all equal. So the length of Q minus S equals S minus P, of course, by construction, and that's equal also to R minus S. Okay. So therefore, distance is sort of an orthogonal separation between, in a separation that's orthogonal to the world line of the particle that's defining the reference frame. The other comment about, of course, is that I said you would want to prove ultimately that clocks exist and so on, and rulers exist. And again, there's a relation between them. If you had one, if you could, there's a model of a clock that people often make is just some solid object, and you send light back and forth between the ends and count the number of ticks. Okay. So in some way, if you can make a model of one, then you can make a model of the other. So now, what is the idea of a reference frame in general relativity? So I think I mentioned before that the whole notion of reference frame is a little bit less useful, or quite a bit, I would say, less useful in curved space than it is in flat. But nevertheless, there is such a notion, and we're always dealing with it at some level. I mean, the Earth's surface and so on, and the clocks on the Earth, they form a kind of reference frame that we can use to give coordinates to the events of space-time. So what's the most general version of this? So we're asking now, not for a mathematical reference frame, but for an actual physical arrangement that can play the role of a reference frame. Well, so we have to think of it as a swarm of particles, one everywhere, each one carrying a clock. And the clock, however, might not be a very good clock. I mean, in general, you might not want it to be a good clock. In other words, it goes always forward in time, but it may not go at the rate of proper time. You could specialize it to be proper time, but we'll see in a little bit that to represent stationary situations, it's often convenient to use a measure of time that's not proper time. In the case where you have a stationary space-time, it's convenient to use what's called killing time, which is the time that makes the stationarity manifest. But we'll come back to that. So what it is, it's a bunch of world lines of these reference particles that fill up the space-time, or the region in which you want the reference frame to be functioning. Then there's this word that people use, congruence of world lines, time-like world lines. You might also, that just means they fill out, there's one everywhere. Time-like. And each with, I won't call it a clock because that's too, I did just say clock, but that sort of too strongly suggests that it would measure proper time. So each one has a time parameter, something that keeps time, marks off some sort of time parameter. And we might as well, since the aim in this case is really, often to assign coordinates, then we might as well give labels to the world lines. So we'll have three labels, I equals 1, 2, and 3, xi, and they'll label the world lines. And then we'll have a fourth coordinate as usual, and that'll be t and the 3 x's. Right? So t will be, so the picture is you have space-time filled by these time-like world lines. Each one of them has time, something to mark off time, possibly in some very irregular way. and these individual lines are labeled by the xi. Okay, and these marks along the world line is labeled by t. So notice that we don't. It's obvious, hopefully from the picture. My drawing isn't that bad, actually. That we're not trying to make these rigid or straight world lines. They're not supposed to be necessarily geodesics. And furthermore, distances between the neighboring particles of this reference frame can vary with time. So in other words, it's not rigid, and it's certainly not rectangular, which it can't be in a curved space. It's obvious that it can't be just a nice rectangular setup, but it also can't be rigid. That's perhaps less obvious, but you might be familiar with that from special relativity. And there are actually there are very few rigid bodies in special relativity. As soon as you try and set a body in motion, say in rotation, then it can't actually remain rigid. So so the reference frame is a much more sort of amorphous kind of thing in general relativity than it is in special relativity. And that's one of the reasons why in general it's not that useful of a concept. Okay, so now given such a reference frame, let's ask, first of all, what kind of spatial geometry will the people who inhabit this reference frame feel that they have? What will they detect? If they measure spatial distances, what geometry will they come up with? So to do that, we need a formula. So now I'm going to assume that we know we've defined a coordinate system here from the reference frame itself. And so I'm going to assume that we know in that coordinate system the components of the metric tensor. So remember, we didn't actually define the notion of tensor and components, but we defined line elements, and we defined this. We did actually define metric tensor as a special case, and we called these 16 numbers the components of the metric tensor. So when I refer to it, that's what I always mean, just this matrix which gives you the line element according to this equation. Okay. So now let's consider these two neighboring observers, as you might call them, or these two neighboring particles. And let's see knowing g mu nu, what distance would they attribute to the between them? So at a particular point event, say p. So remember, distance is measured by something orthogonal. So let me call this infinitesimal displacement along the direction of the world line of the particle of the reference frame. Let's call that dx, and let me call. So let's call that dx, and let's call the infinitesimal displacement that takes this point p to some point on the neighboring particle. Let's call that delta x. Okay. Now we just saw that if this is to be a measure of distance between the two, then dx must be orthogonal to delta x. Actually, well, okay, leave it like that. And this thing has coordinates xi, and this has coordinates xi, then plus delta xi, right? So what's the condition on this delta? So what we're really looking for is where along the neighboring world line do we get to if we go orthogonal to this first world line. So we want to know the value of x0 along this, that is the time coordinate, along this neighboring world line. And how do we find it? From the orthogonality. So these by assumption have to be orthogonal. That's true if and only if g of dx and delta x is 0, right? And that means g mu nu dx mu dx nu, delta x nu, sorry, should equal 0. So let's expand that out. G00, I'm thinking, well, we'll leave it like this. So let's expand that out. Then we get dx0, delta x0, or delta t, I could have called it, plus g0. Now, dx, obviously, what can we say about dxj? Dxj is 0, of course, because it stayed on the same world line. So we only get the term from dx0. So it's g0j dx0 delta x j. And now the other two, the purely what's left over is the purely that's the 0 here. And then what's left over after I take that 0 into account are the purely spatial ones. But again, that has a 0 because dxj is 0. So this whole thing is required to be 0. And so it means if we divide through by dx0, it's giving us delta x0 is equal to minus g0j delta xj over g00. Right? And this, so that's, okay. And in a special case, if it's always relevant to think of the special case where the clocks are good clocks. As I said, we can't ever make the reference frame rigid in general, but we can certainly allow the clocks to be good clocks. If they are good clocks, then G00 is just minus 1, and then it just becomes plus G0j delta xj. So that's if good clocks, which means G00 equals minus 1. So now we can get the spatial line element. That is, tells us the infinitesimal distance in this reference frame between these neighboring nodes in the reference frame, or particles. So what is it? So it's that would be delta s. That's the. So I keep having these pangs of conscience that I should have called this. I think I'll finally give in to them. I should have called this here just to emphasize the geometrical character. I should have called them dp and delta p. So this would be dp and delta p, leaving dx and delta x for the coordinates. It's a kind of pedantic restriction, but anyway. So we want these infinitesimal tangent vectors to actually be orthogonal. And then in our coordinate system, which is defined by this reference frame, this is the condition. Okay. So now delta s squared, which is the length of this infinitesimal displacement, will be, as always, just given by g mu nu delta x mu delta x nu, right? And now I just have to work out what that is. It's g00 delta x 0 squared plus 2 g0j delta x0 delta xj, right? Because I could have taken those two in either order, plus gjk delta xj delta xk. Just the sort of naive spatial metric that you would get if you just drew a line of constant x0 and asked what was the metric of that hypersurface. But that's not the physically measured distance between the neighboring nodes of the reference frame. So just plug in what this is. So it's G0, 0. We just saw what delta x0 was. So it's G0j delta xj squared over G0, 0 squared. So it becomes like that. Then we have the same combination, G0j delta xj times delta x0, so it's a minus. It's another factor of this. It becomes squared over G0, 0. And there was a factor of 2 out in front. I don't need 2 minus signs, but I do need the factor of 2. And then the same thing here, coming that same term. So these two terms are equal up to a factor of 2, so you just get minus this. So the answer is gjk delta x j delta xk minus g0j, let's expand it out, well, delta xj squared over g0, 0. So if we wanted to ask what is playing the role of the purely spatial line element, we just need to, in fact, we need to take out this delta xj, delta xk, and we get gjk minus g0k g0j over g0, 0. I just split this up into two factors and gave one the index j and one k to avoid collision of indices, and then it's delta xj delta xk. Okay. So that's, we might call that, just to give it a name, delta L squared, meaning just some name for the line element, the spatial line element in the reference frame. And that's the result. Again, if it's in the case where G0, 0 equals minus 1, it simplifies just slightly. Well, there's no need to really write down. It's obvious what it simplifies to. So one comment here is that this combination, actually, you might or might not be familiar with this, but you can check it. This combination is actually the inverse. You see, this has the indices downstairs. This is actually the inverse of the spatial part of the inverse of the metric. So actually haven't, funny, did we define? I don't know that we actually, I mean, I'm sure everyone knows the definition, but I just don't remember having defined the inverse of the metric. Well, okay. So, just for completeness, as everyone knows, this is the definition of the metric with the raised indices. Okay. So the point is, if you take the four-dimensional metric, component metric tensor matrix that represents the metric tensor, if you take that four-dimensional matrix, invert it, pluck out the the corner of it, which is just referring to space, and then you re-invert that, you will get, that's what this funny combination is. And later on, we may see why that, from a geometrical point of view, why that had to be true. But just for now, it's just an observation, a comment, which you might like to check. It's part of a more general mathematical relationship that is often useful, which is how to relate the inverse of a full matrix to the, if the matrix is split into block matrices, how to express the inverse of the large matrix in terms of the inverses and other properties of the block matrices, or vice versa. So this is a special case of that kind of general formula. Anyway, from a physical point of view now, well, so now we have found one thing. We found that the spatial metric in general will not be curved, even if, suppose you're in flat space, as long as these are not geodesic world lines, as long as they're not straight lines. In general, there's no reason that this thing would be constant. And so in general, you're going to see distortion of spatial metric depending on the choice of the reference frame. The other striking thing about this is that it shows that so this is yet another reason, if you like, why reference frames don't show up so much in discussions of general relativity as they do in special relativity, is that it's impossible to synchronize clocks in general. So if you think back to the cases of special relativity, there's a big, like in the textbook kind of derivations of the Lorentz transformations, there's a big discussion of how you should synchronize the clocks. In fact, it's supposed to be the case, although I've only heard this, I haven't directly checked it, but it's supposed to be the case that one of the important motivations for special relativity historically was people had to learn how to synchronize clocks for the purposes of trains running through France and other places. That, in fact, Poincaré was supposedly on some commission for synchronizing clocks, exactly, that the government had appointed. So then he just applied the same methods, I guess. But that's something, so the synchronizing of clocks is something that you can do in an inertial reference frame in flat space, but it's something that you can't do in general in a reference frame in curved space or in a non-inertial reference frame, even in flat space. So now, for this point, we'll consider, since we're interested in actually synchronizing real clocks, we'll consider the special case in which the time coordinate is clock time or proper time along the world lines. So what would it mean to synchronize? When we say that we can't synchronize clocks, what are we saying? So it could be that all of us are part of the reference frame. Each of us is a particle in the reference frame, and we each have our clocks. And now you and I are close to each other, and we say, okay, 3, 2, 1, and we set our clocks, and then you synchronize your clock, and you synchronize, and you synchronize, and then well, we don't quite have enough to make a loop, but someone comes back, and then I find that my clock is not simultaneous with that there's some gap in the time. That's what it means to not being able to synchronize clocks. If for every closed curve I took within the space, that is within the set of particles, I found that there was consistency, then I could have a global time in which everyone's clock was synchronized. But what this is really saying is that's impossible. What it's saying is that local synchronization doesn't lead to any consistent notion of global synchronization. So how can we see that? This is what obviously people who design something like a GPS have to take account of. They can't hope to have local. So there's a slight mismatch in the local times that the GPS is assigning to events in the neighborhood of the Earth. So how do we see? So let's go back to this exact formula that we had before. What we did here was find what event Q, let's call it, in the neighboring world line is simultaneous in the reference frame of this reference frame with respect to the four velocity of this reference frame particle. We found that point Q that was simultaneous to P, because remember, simultaneity means orthogonality, obviously, in this local reference frame. So, and we found the formula for delta x 0, we saw that it wasn't 0. So that means if to the extent that it's not 0, it means that the clocks are not synchronized. Whatever when the clock at P, if it reads 0, the clock at Q reads delta x 0, which is not 0 in general. So what is it? It's minus G0J delta xk, delta xj. And I think plus now because I set G00 is minus 1. Okay. So that tells us how much in this particular reference frame things fail to be synchronized. So now let's look. So let's take let's take our reference frame again. And this is a picture in space now. This is not the picture I'm always drawing of a space-time manifold. This is just space. It's just this sequence of the particles in the reference frame. And we want to know how much this delta x accumulates as you go around, and you find that that will be the integral around the whole curve. So let's call it gamma. This is now a spatial curve, though, not a space. It's not a time-like curve as it's often been. Around that curve gamma of delta x 0. So, and that's equal to the integral of G0J delta xj along the curve gamma. But then this will look familiar to you. This is just, forget the 0 here, this just looks like some components of some vector dotted into, this you could think of as vector potential or the magnetic field or something like this. Then you apply whatever that theorem is called. What is it? Green's theorem or someone's theorem? Which is it? It's a line integral, yeah. This line, I want to convert it into a surface integral, yeah. I want to, Stokes theorem? Anyway, one of those.
Stokes converts
volume to surface. I think, well, Gauss's law and Stokes' theorem, I call them all Stokes' theorem, so I can never, I think you're right, I think Stokes, anyway, everyone knows this one, whatever it's called. I think it's some combination of Green, Gauss, and Stokes. And probably in French it's a different name altogether. But it's Green also.
I think
It's always Stokes. Okay, so whatever it is, we can convert it into this volume integral, which is which I'll write in this way that might look slightly unusual to you. Partial j, we have to take the curl, which is, the partial derivative of this object with respect to the spatial coordinates, anti-symmetrized, and then you have to integrate it. Normally, as you see it in, I think in textbooks of electromagnetism, you dualize this and turn it into a vector, but I'm leaving the components of what this really is, which is called the 2 form. And then there's a sort of component of the surface element. It's not important that you understand exactly this notation now. We'll come back to it later, because you can put it in any form that you're familiar with. The important thing is that this thing, this curl thing, it's sort of the curl of G, spatial, this object whose components are G0J, that's not equal to 0 in general. There's no reason that it would have to be 0. And when it's not 0, then it means that you just cannot synchronize. When you go once around, you're going to, if you try to synchronize, you're going to find that the time that you come back with is not your own time. It's displaced by this amount. Okay, so I think maybe we'll make an example of that for a homework problem or something, but hopefully the result is clear. So now we saw that you can't synchronize in general, or almost never. If you demand local synchronization, you can't have it. But there are situations in which there's a natural choice of global time, even though it may not exactly agree, and will not in general exactly agree. It will not result in the perfect local synchronization. And we already saw one example of where there is a natural choice of global time. That's when we were doing cosmology, right? Yeah.
I'm sorry, I don't understand how that line integral converted to a surface integral proves that you can't have it.
Oh, it doesn't prove it. But if this curl is not zero,
Right.
then you can't have it. It could happen that this curl was zero everywhere.
But why does the curl not being zero prove?
Well, if the curl is not zero, then let's take a very small curve.
Okay.
Then within that region, the curl will be approximately constant.
Why?
And then this failure, this asynchrony, this lack of synchronization, this measure of how unsynchronized you are, will just be basically given by the value of that curl times the area of this little region. And that will not be zero. I'm not sure what you're asking. Maybe I thought you were worried that maybe even though this is locally not zero, the integral could come out to be zero. Maybe that wasn't your question. That's true.
How is it a measure of non-synchronized?
Oh, I see. Why is it that the delta x0, that the line integral of that being non-zero, means that you don't synchronize the clocks? That's the question. Oh, I thought you're okay. Well, if you do synchronize the clocks, then when you go from one point of the reference frame, one node of the reference frame to a neighboring one, then the change in time that the moment of that clock that's actually synchronized with this clock locally will be offset from this by delta x0, right? Okay. And so now we keep going, and then finally we find that my own clock, when I come back to me, my own clock is offset from, in order for everyone to be synchronized, will be offset from itself by some finite amount. So I'd have to readjust my clock. But then I can't, this person could readjust his or her clock by just setting it forward by delta x0 or whatever, and then there would be a synchrony. Okay, so they could certainly do that. That would change the reference frame. But the one invariant thing that you can look at is when you go around the whole curve, it doesn't matter how anyone resets their clock. If my own clock has to be reset by a finite amount, then I'm in trouble, because it's not just resetting the zero. It means that no matter where I set the zero, when I come back, it's not right. Is it clear? Yeah, maybe someone else.
Does this not violate the transitivity of synchronization?
It certainly does. It certainly does, yeah. I mean, that's another way, you could say it that way.
But there's
synchronization is not transitive.
But even a neighboring point isn't quite synchronized, because it's delta x0.
Well, I see the word. Yeah, it's not synchronized. That's right. So this person hasn't set their clock right. But they could just reset the zero of their clock, and then it would be synchronized. So we're just asking. Another way of asking it is, at what clock reading should this person choose to zero their clock in order for this to be synchronized? And the claim is, well, if this person chooses, if they set the zero, if they say that 3 seconds really should be reset to zero, then we'll be synchronized. These two will be synchronized. And then this person will say, okay, now for 5 seconds, I'll redefine t equals 5 to be t equals 0 by an offset. And then we'll all three be synchronized and so on along this line. But finally, when I come back to myself, we have to say, I have to redefine my t equals 10 to be t equals 0, but then I've messed up t equals 0, right? So I'm not in synchrony with myself. And the amount, it should be stressed that the amount by which it fails depends on the curve, as you see here. Depends heavily on the curve. Yeah.
So maybe the situation could be clarified by including one word. It remains possible to synchronize clocks pairwise,
Right.
but it is impossible to globally synchronize clocks.
Yes, that's
And
right.
At the end of the day, the configuration you talk about in your closed loop,
The
that's
magic word was globally.
global,
Right?
yeah.
Yes.
The closed space-like loop, that's just a measurement configuration for time curvature. So pairwise, each two clocks can be synchronized as we do it in special relativity.
That's right.
However, in a global loop, it's impossible. The
Yes.
same thing happens to spatial curvature. Of course, even in a curved space, we can intrinsically build straight lines. However, we don't need to expect that something like a circle in a curved space always closes.
Yes. Yeah, absolutely.
So synchronization is possible,
even
however,
closer
global
analog.
connection does not exist.
Yes, does that help? Yeah.
This curl would be non-zero for all curved geometries, or there are some curved geometries where.
Oh, there are curved geometries in which this can be chosen to be 0. So that's what I was about to say. So we already saw one with the cosmology, right? So everyone can synchronize their clock in a natural way in that kind of geometry. Another one where it can be done. In fact, let me say a whole class of ones, which is where it's important to actually choose such a time, is
Could you
that
choose some coordinate system where the curl would vanish? Is that possible?
could you? Well, so that's a good question. You might think that it was possible, but we just saw what this curl means. It represents the failure of synchronization when you go around an infinitesimal circle. Okay, and so that's all to do with physical things. So when you say choose coordinate system, it depends what you mean. We've given ourselves the reference frame here, the particles of the reference frame. So basically that means that the xj's are not, they're not free, they're not at your disposal. But we also said that the clocks here read proper time. So that means that the x0 is also not at your disposal, except an offset. The absolute choice of 0 can be changed, but otherwise it's not at your disposal. So the question would be, as long as we're fixing our reference frame, the question would be, can I choose the offsets and such? Can I displace, can I make a transformation x0 goes to x0 plus some function of offset that depends only on the world line I'm on? Can I make this go away? Actually, you see here that you can't because there's no x. There's no. Let's see. Do we see it? Well, I'll leave it as an exercise to prove that you can. But we know physically that you cannot because all we did was talk about synchronizing of clocks, sending light signals or whatever. It's all physical operations. So the choice of that coordinate can't possibly affect it. What could, maybe you might make an exercise, see how the metric coefficients would change if you make this is kind of an analog of a gauge transformation. It's very much like an analog of a gauge transformation. This is going to be something like the field strength. If you want to check it out mathematically, you could do it that way. But as I've just argued, it won't do you any good. The line element is some invariant thing. It doesn't depend on how we set the zeros on the curve. Right? Between any neighboring ones, it depends heavily. Delta x0 will be modified between neighboring ones, or between two distinct ones, but between one and itself, going around a particular curve, then it can't be modified by this, right? Because delta x0 will go to delta x0 plus, then it'll be delta of f of xj. If in this delta it means going from one world line to another, this f can change. But when I'm going from the world line back to itself, then this delta f is 0.
Just for clarity,
So, yeah.
are these curves, are they closed space-like curves? Are you talking about comparing a point to itself, essentially? A space-time point to itself?
Yes.
Oh.
The curve, it's not important. If you're going to, the curve is a curve. It's not quite the right answer. The curve is not a space-like or a time-like curve. It's a curve in the 3 space defined by the coordinates xj. In other words, it's a curve in the set, in the space of curves.
So constant time slice.
No, it's not a constant time slice. No, it's not. No, it has nothing to do with it. But it does have to do. It can be actually any slice at all, and any. That's exactly what it can't be in some sense. The statement that you can't synchronize means that you couldn't make. If you have this reference frame like this, and you were to follow synchronizing like this, it would not come back to itself. That's what it means. So there is no natural notion of time with respect to which there would be a constant time size. But of course, you could use it to be a constant value of x0, but that's not the physical meaning of what we're doing. The physical meaning of what we're doing, we're starting at some event in space-time along some chosen, say, origin of the reference frame. And then where we go is entirely determined by this orthogonality relation, by this local synchronization. And so it'll just bring you to some other point. Is it clear?
So your path gamma is defined by the local synchronization?
The path gamma is defined by, well, if I had to define it exactly,
I can't just take any closed loop?
any closed loop in the space of x's, but then the actual path, regarded as a space-time path, you have to follow the local, you have to follow the, curve that's swept out by the synchronization. Okay, so what you have, this reference frame consists of a bunch of world lines, right? We started at one particular one, and so now we're going to an adjacent one, and we'll come to a particular location there, and then we'll come to a particular location there, and a particular location here, following the synchronization rule, and finally we'll come back. Oh, I see the problem you're worried about now.
I think what we're confusing here is global time and local time. You have a time coordinate x0, and you also have the idea of keeping track of time. And so what you're saying is if you do a closed space-like curve, using this rule of transferring time, using local synchronization, you're not going to come back to the same global time. Or sorry, the curve is closed in the global time, you're not going to have a zero local time change. It's going to be a non-zero change in
that I don't know. If it's closed in the global time, that would mean that it wasn't correctly synchronizing the neighboring things. But if it was closed in the global time, that would mean when you came back that x0 would be the same as where you started.
Yeah.
And that's local time. That's also local time.
So then-
x0 at that curve would be local time.
This closed loop then is just saying, coming back to your same x coordinates.
That's what it means. It means coming back to the same x coordinate.
But
It means
the-
coming back to the same particle in the
The
reference
same world
frame.
line,
The
essentially.
same world line.
Okay.
Another point on the same world line.
All right.
That's exactly what it means. And the statement that it is not possible globally to synchronize clocks is the statement that in general you won't come back. You'll come back to the same world line, but not to the same point on the world line.
So physically, you don't even come back because you cannot start. You would have to move faster than light. It's only there.
This is not a motion of something.
Yeah.
This is absolutely not a this is a synchronization.
Yes, yes.
Right? So that's, yeah, you'd have to move infinitely fast in that frame in order to follow this thing.
It's the evaluation of time-like curvature along that configuration.
Yeah, if you'd like to give a name to time-like curvature. So I think maybe we should make a homework problem on this, working it through. The simplest case is like just a rotating. Imagine a big stone, something or other, like wheel or something like that. And imagine that's your reference frame, and you set up clocks everywhere. And now you start the wheel rotating. What will happen? What will happen to the synchronization of the clocks along that wheel?
Can I give an example of geometry, curve geometry, where the curve vanishes?
I'm going to give an example now where so there's a whole class of things where, first of all, there's a class of things where there's a natural choice of time, and those are called stationary spacetimes, or stationary metrics, or stationary gravitational fields. Those are ones in which, in some sense, nothing is changing. The technical way of saying that is, that we'll say, we don't know yet what this means, but the technical way of saying it is that there exists a time-like killing vector. I won't try and define it more what it means right now, but what it means is there's in language that everyone would know, it's a time translation symmetry. So there's some way of sliding the space-time along itself in a time-like direction so that the metric doesn't change. Since we haven't defined killing vector and so on, which is an infinitesimal symmetry, a generator of a symmetry, we can say it this way. What it means is it could happen that the metric coefficients are, which a priori depend on x0, x1, x2, and x3, that they don't depend on x0. Right? So that's all we're saying. They're independent of x0. You can find some reference frame in which that's true. Oh yeah, I wanted to say something in answer to one of the questions that came up here, which I forgot to say, which is that, as someone asked, I forgot, I think you asked, could we find coordinates in which this curl would go away? So once we've chosen the reference frame, we cannot, because the coordinates are tied to the reference frame. But you could ask, could I find a totally different reference frame? So set everyone moving in a different direction, choose a different set of world lines, and maybe different clock settings along the world line. That's a more general reference frame. Could I find one in which this will go away? That's certainly possible. There are cases in which, like flat space, in which you can find, just use your usual inertial reference frame and this will go away. And yet if you use a different reference frame, it's not zero. Like the one that we just talked about with the rotating stone or the rotating platform. So just because it's not zero with one reference frame doesn't mean that it has to be non-zero in every reference frame. But in general, it will be non-zero in every reference frame. Almost, well, every good reference frame. In general, the reference frames where it's zero will go singular at some point. You get a collision of the particles making up the reference frame. And here's an example where So this is a slight, at the moment, it's a different consideration. We're talking about stationary spacetimes, spacetimes in which nothing is changing. Now, within that, there's a subset which are called static spacetimes. Now, I have to warn you, this is a special way of using words that's common in relativity, but maybe not used everywhere, where you distinguish between stationary and static. Again, I won't actually define what it means now, but I'll just, in the most general way, but just give you something to think about that will illustrate the difference. So consider two spacetimes that have stars in them, like the sun. In one of them, the star is at rest, it's not rotating, and in the other one, it's rotating. The spacetime, like the sun really is, right? The spacetime where it's not rotating is called a static spacetime. That's why it's called static, because basically nothing is moving. However, if it's rotating, it's still stationary in the sense at a later time you have the same setup as you had before. The sun is turned to a different place, but if you imagine it as a perfect fluid, then that's not a real change. And in any case, the metric, whether or not you want to say that the sun has changed, the metric has not changed because you still have the same mass of fluid distributed the same way and rotating with the same velocity. So that's stationary, but it's not static. Now, stationary spacetimes have the property that you can choose the coordinates by definition such that this is true. Static spacetimes will have the property usually that you can actually choose the coordinates so that this curl goes away. So in the static spacetime, you actually can find a global synchronization. Gesundheit. What it means geometrically is you can find a hypersurface that's everywhere orthogonal to the world lines of the reference frame. Then, of course, if you go along that hypersurface, then by what I just said, everything is synchronized. I mean, you set the clocks at 0 everywhere on that hypersurface. But in a rotating spacetime, or a stationary but not static spacetime, it's in general impossible to find a surface which is orthogonal everywhere to the world lines of the reference frame. And therefore you can't really globally synchronize time. That's the more geometrical way of thinking about it. That wasn't actually the main point I wanted to make. The main point that I wanted to make was that in the stationary space, the existence of stationary, the special case of stationary spacetimes is very important, obviously, because many things are very close to that, like our solar system is very close to that. And when you want to describe a stationary spacetime, it gives you a good reason to consider clocks which are a time coordinate which is not proper time. So why is that? Because there's a conflict between choosing a time coordinate that will exhibit the stationarity as it's done here and choosing one which reads proper time. So if you choose your time coordinate to read proper time, it in general will not exhibit the stationarity. So how can we see that? So suppose this is a set of time coordinates that does exhibit the stationarity. This is our reference frame. Okay. So even though the metric is stationary, that says nothing depends on t and x0. But it doesn't say that nothing depends on xj. In general, it will. So if you go from one world line to another, the value of the metric coefficient will in general change. And so in general, in particular, g00 will change from one to another. g00 here will have a different value than it has here. Because it's stationary, it'll have the same value everywhere along each world line. But when you go from one world line to another, it'll change. But what does that mean that it changed? That means that if we go a fixed distance in the t coordinate, we've actually swept out a different proper time here than we have here. So that means these clocks are not reading proper time. this time coordinate is not proper time. So if you want it to be proper time, you'd have to change. If you want it to be proper time, you'd have to change. So suppose G00 is bigger here, or whichever way it should be. I won't try and think now which way it should be. Then the surfaces of constant proper time will look something like this. Right? They'll deviate from the surfaces in which the metric coefficients are constant. So if you're describing a stationary spacetime, it's often convenient to use a time coordinate, which is not proper time. That's the main point. But so in this one, in this orange one, G00 is equal to -1, but partial G mu nu partial x0 is not 0. So that's the trade-off. Now this fact that we just looked at this happens in the neighborhood of a star, for example, or in the neighborhood of the Earth. And in fact, it's closely connected to the gravitational redshift. It's almost the same thing as the gravitational redshift, which is, from a certain point of view, it's telling you that clocks at different locations in this gravitational field are running at different rates. Different rates with respect to the natural global time. Different speeds. So we'll come back to that. But before doing that, so let me stop. There's been a few questions. So now I want to discuss about geodesic motion, how it looks in this. How do we describe geodesic motion? But is there any more questions on this?
It goes back to the start of class, essentially. You're saying that an integer on every point is indistinguishable from Minkowski space. Is this also true in space-time to have cosmological constant?
They have, sorry, what?
A cosmological constant?
Yes.
Oh.
Yeah.
There's no implicit curvature in those spacetimes?
Spacetime with a cosmological constant, if you depending on the matter content and so on, or if it's just empty space other than the gravitational field, then the Ricci scalar cannot vanish. So what's called, and we'll see what that is, but some component of the curvature tensor cannot vanish. So there's curvature, but that's a crucial question. The existence of curvature is not meant to be incompatible with this statement. If it were, then we would rule out every interesting solution, whether or not there was a cosmological constant. So that word infinitesimal is crucial. It's only sort of to leading order that it's indistinguishable. If you look at higher order, then you start seeing the difference, and that difference is a measure of the curvature.
So are there no regions where you can't make a coordinate station to look locally like Minkowski? Like in a sphere or inside of a horizon or something?
Can there be flat regions?
Can there be regions that can't be made flat?
Yes, most regions cannot be made. Oh, you mean even locally?
Even
infinitesimal neighborhood. You mean, is this really true, in other words, what I said? Well, that's a good question. So you can imagine spaces in which it's not true. And then the question is, are they allowed physically? That's really what... According to the rules of classical general relativity, they're not allowed. But maybe in quantum gravity, maybe they are allowed. So what would be an example of something, a space-time like that? An example would be a cone, right? The simplest example you can think of is a cone. So there's one point here, obviously, whose even infinitesimally the neighborhood is very different from a portion of flat space. And this is in fact this is it's another story entirely, but maybe it's worth saying. If you want to work out the temperature of a Schwarzschild black hole, so the Hawking temperature associated with the black hole, one way of doing it is by doing an analytic continuation to the metric. And then you have to do you have to make a periodic identification in T after you do the analytic continuation. And with what period should you identify? And the answer, that period is the temperature, or the inverse temperature. So that's giving you crucial information on what the temperature is. And how do you choose it? Well, you choose it precisely that you shouldn't have a conical singularity like this. Sometimes it's called, I think this word is maybe an older word, and I might have not remembered it right, but I think the word might be elementary flatness. So that might be the name for that condition, right? And in particular, it excludes conical singularities. And there it gives you an important physical bit of information. So whether it's really true in the case of quantum gravity that we need to consider only space-time through which this is verified, that's a very much an open... I mean, chances are that we have to go beyond this. But within classical general, I mean, we probably have to go well beyond it and consider things that aren't space-time at all. But to the extent we can approximate things by still talking about continuum space-time, it's very likely we have to weaken this. But in the context of classical general relativity, it's assumed, seems to be correct, that we do always keep this.
I guess that's just a statement that it's a Lorentzian manifold. So
that's exactly what it is. That's part of the statement that it's, or that is basically the statement that it's a Lorentzian. Right.
So that it has to be differentiable, essentially.
Well, first it has to be differentiable, but then, But the statement is that what has to be, it's not that the manifold itself has to be differentiable. That's true, but it's not, it's less than this. This is the statement that there has to be a well-defined metric tensor everywhere. That's really what that statement is. And then generally you want more. You want this to be differentiable, so that's a higher degree of smoothness that you're imposing. Here there's not even a well-defined metric tensor, right? Because if there were, then, well, anyway. For example, the angles around this point don't add up to 360 and so on. Okay. So, well, let me make a start anyway on geodesic motion. Trying to speed up a little bit. So this is another thing. So remember, we're looking at not just reference frames, but more generally how the value that the metric has, what the metric actually is, how it influences the behavior of matter. And then conversely, you can use that to explore the nature of the metric you have. Like when we work out the orbits of the planets, or when people found what they were, they're in effect learning something about the curvature of the space-time metric in the neighborhood of the sun, and so on. So geodesic motion is both very important as a probe, and it's very important just because a lot of things are moving essentially geodesically. So the next thing I want to look at is geodesic motion. Then we'll come back and how it's described. What is the equation of motion for a particle following a geodesic world line? Then we'll actually come back and talk about the effect on clocks more, the gravitational redshift. So let's look at the case of a massive particle. So that means a particle that's following a time-like world line. If you want to consider photons as things going at the speed of light, then you need a sight. You can't do exactly what I'm about to do. We're still using a coordinate chart, as we've been all day, and most of last time too. So how do we get the equation of motion of a massive particle? So this is just, of course, it's another input to the theory. Again, it's an input at this stage. If ultimately you don't have point particles in your theory, then you need to regard this as an approximation. It needs to be then justified. So in classical relativity, as you might know, you don't really have point particles because they would collapse. They would be surrounded. They would become a black hole. Right? But we can imagine it as a probe, or what's sometimes called a test particle, something that is a point particle. So maybe I should write that word out, test particle. Meaning one that we neglect its influence on the gravitational field. We think of the gravitational field as fixed. and just use it as a test or a probe. So in that case, the assumption is, which is just copied directly from special relativity, is that the action, there's an action principle, and the action is given, this, I assume that this is familiar to everyone from special relativity. So it's just the action between 2 points on the world line, say 1 and 2, is just the elapsed proper time scaled by the mass. Okay. So what's the equations of motion, though, for this? I'm clearly not going to finish deriving them. So the question is it worth starting? Yes, it's worth saying a certain thing. So now we have to talk about this. I think someone raised this question before in relation to some, I forgot why, but actually the homework, I think. Yeah. How do we, what mathematical technology do we use in order to express variations of the world line? Well, what the statement is here, when we write this action principle, it's to be understood that we take a finite bit of the curve and the initial and final endpoints are held fixed. Or if you like, you take the infinite curve, but you're only allowed to vary it over a finite region. And then the action, in that case, the action should not change. It's very important, it's very useful to see what happens when the endpoints do change. That gives us a definition of momentum. So I'm going to consider varying the action under general variation, but when we want to get the equations of motion, we'll put in the condition, we'll only demand that the variation vanish when the variations vanish at the endpoints. Now, how do we express the variation in a convenient way? So we can work out, we can give meaning to this variational derivative, as it's called. So I'm going to work with just the rescaled action by minus m, just for convenience. And that's, again, it's the integral from 1 to 2 of minus g mu nu dx mu dx nu, okay, square root, that's the variation of d tau. For the moment, to avoid having to deal with infinitesimal things, make it look more comforting or something, I'll multiply and divide by delta lambda. Of course, there's a delta square root here, so they cancel out. Now we're just dealing with derivatives, and it's the usual story that x mu is equal to gamma mu of lambda in the coordinate system. Because I'm doing everything in a coordinate system. So I'm not going to be careful about p and x and so on, like we were when we were talking about manifolds in general. Now this is a path. No, this is a path, and if you want to be very careful, you should also say, not any function can be a path, but it has to be something that's one-to-one correspondence between the parameter lambda and the point on the path and so on. But you can just take that. No one is likely to assume anything else, so there's no need to be all that careful about saying it all. But what we do have to be careful about is to say, now how do we vary the path? Okay, so now we want to consider a second path, again parameterized by lambda. We could actually take this, once we have this parameter, lambda, we can actually put here, well, instead of writing the integral from 1 to 2, I can interpret that to mean lambda equals lambda 1, some fixed choice of lambda 1, which could often just be 0 and 1. Okay. But how do we vary that? We have to say that there's a second, there's a one parameter. If just as we defined a vector, when we had to define a tangent vector, we got it from a curve. In the same way, what we were doing there was taking an infinitesimal variation and relating it to derivative along a curve. In the same way here, we can take a curve of curves. We can introduce another parameter. There we introduced a parameter lambda for the curve. Here we have that same parameter. But now we can introduce another parameter independent of that, which labels which curve you're on. I'll call that mu. Oops, no, I won't call it mu. I don't know why, but I've called it r. So this r is another real parameter. So when r equals 0, we have our original curve, let's say, and when r is some infinitesimal number, very tiny number, we have a curve that's very, very close to the original curve. And so now we can talk about the two kinds of variations, the two kinds of changes that are important here. One is dx mu, which is just the dx mu that you see here. So that's just partial, if we like, dx mu d lambda, if you like, is partial gamma mu, well, let me write it. Partial gamma mu of lambda and r times d lambda. Okay, so that's our dx mu that we used here, that we've already seen. But there's a second variation which comes from holding lambda fixed, but varying this auxiliary parameter that we've introduced, which is r, right? So I'll give another name. This often used for variational principles. This delta, little delta. So what delta x mu is the same thing, only switching the roles of r and lambda. So it's equal partial gamma mu of lambda and r partial r dr. Right? So those are our two variations. What we'll be doing when we vary the action is apply this delta variation to the integrand here. But what will be crucial, what we'll use heavily, and so it's very important to notice here, is that these two variations commute. So in other words, why is that? Because one comes from these are partial derivatives. One is differentiating with respect to lambda, one with respect to r. And partial derivatives commute with respect to distinct variables. So that's the main thing. It's really to prove that I introduced this more careful notation. If you're just willing to assume that the two variations commute, then you can just proceed directly. So let's just draw a picture of what's happening here. Here's my curve gamma, and here's my curve gamma plus variation of gamma. Here is my vector dx, and there is my vector delta x. So the delta x is sometimes called a connecting vector. It's taking you, here it's of course an infinitesimal displacement or vector. It's taking you from one curve to the neighboring curve. Whereas dx is taking you from one point on the given curve along the curve to a neighboring point on the curve. So now that we have that, we want a variation of s over m. And I'll just write this out, then we'll have to quit. It's equal to the variation. We now have to vary this expression under the world line, right? Which is d tau. So it's that same expression, instead of just the usual variation of a square root, it's 1 over that, and then we have to take the variation of what was under the square root, which was g mu nu. I'll put here x, because that will be important to remember. Dx mu d lambda dx mu d lambda. So we have to now vary this thing, and we'll get three kinds of contributions. One from varying, of course, when I write this, x is gamma, as always, of lambda and mu and r. We'll get three kinds of variations. One from varying x here, and then well, really two if you like, and the other one from varying the derivative of x. And here's where we'll use that the two variations commute. So we'll be using that the variation of d of x mu is the same as d of the variation of x mu. If you like, you can divide by d lambda in both cases. So that's the crucial thing. Once you know that, then it's a simple matter to carry out the variation and do an integration by parts. And we'll do that next time.